Okay, I can only see one screen. We have to live with this for a while. I don't know why it's the case. So unboundedness, let me draw it here then. You have our feasible region. Feasible region should be unbounded for us to have an unbounded solution, right, of an LP. If the feasible region is unbounded and you give me an improving direction, C, which takes you in the indefinite region in the feasible region, this is a Q for unboundedness, right? How do we detect this? Using the simplex method, because we won't be having the graphical solution at hand. So you have to detect this using the simplex method. So any ideas how we should detect it? So remember our formula. Let's go back to our formula. Our formula over here, change in the objective function is the coefficient of the entering variable times the result of the ratio test. Okay? So if I have an entering variable, which will improve my objective, and if my ratio test tells me that there is no finite bound, so you can make the entering variable any value you like, any large positive value you like, you won't be leaving the feasible region. That's your Q for unboundedness. Does it make sense? Okay, so that's how we will see unboundedness. Let's look at this example. If you draw the feasible region, you will see directly that it is going to lead you to an unbounded solution. So in order to apply simplex method, what do? I have to translate this to the standard form by adding slack variables. Let's call it S1, making this an equation, by adding another slack variable S2, making this an equation, right? And writing this in row 0 format, so z minus x1 minus 2x2 equals to 0. So I have standard form, I have S1 and S2 as my first basic variables. This is going to be a very easy LP to apply simplex for, right? So if I apply simplex method, let's do it here. I don't have room, sorry. So I will have 1 minus 1, 1, 0, 10. 1, 0, 0, 1, 40. S1 is my basic variable here. S2 is my basic variable there. And I have my objective function in row 0 format, 0, 0, 0. Correct? These are my basic variables. Sounds good? Okay. So what will I do in my simplex iteration? I will enter the most favorable variable, which is x2 in this case. I will do my ratio test, right? What will be my ratio test result? It's minus, which means what? So remember, what does ratio test tell me? How much? Currently, you have a solution. Your solution is, let's look at the current solution. x1, x2, s1, and s2. Current solution is 0, 0, 10, and 40, right? This is your starting basic feasible solution corresponding to the origin in two-variable case. So you ask the question, is there a favorable variable to improve from 0 to something higher and get to a better objective function value? Both x1 and x2 are eligible, and x2 has a better objective function coefficient, so you want to make x2 as high as possible. Okay? But if you make x2 higher, the question that you'll ask is that, okay, the other basic variables are going to change. I don't want to leave the feasible region, so I do my ratio test that tells me the largest possible value that x2 can take without leaving the feasible region. But if I look at my equations, governing the relationship between x2 and my current basic variables. If I do my ratio test, what will I see? Oops. Okay, what will I see? Let's look at the first equation. I have x1 minus x2 plus s1 equals to 10. Okay, x1 is going to remain non-basic. I can forget about it. I asked the question, how much can x2 go up without hurting the non-negativity of s1? But s1 is simply 10 plus x2. So no matter how high x2 gets, s1 will not be negative, right? So there is no bound coming from this equation in terms of the ratio. There is no ratio coming from this equation. Does it make sense? So if you look at the ratio, you have 10. You divide by the coefficient of the entering variable, but only if that coefficient is positive. If it's negative or 0, that means that there is no finite bound coming in the ratio test. Does it make sense? Same thing for the second equation. Second equation tells you that you have x1, x2 does not appear there, plus s2 equals to 40. x1 is going to remain at 0. S2, no matter how high your entering x2 variable is going to stay at 40. So in other words, you can change x2 indefinitely without leaving the feasible region. And per unit, you have improvement in your objective function by 2 units, which means that you can improve your objective function indefinitely. Does that make sense? Is that clear how we arrived at an unboundedness point? Using the simplex method, there is an entering variable. That entering variable per unit improves my objective, but there is no hindrance in terms of the highest possible value that this entering variable can take. It can take indefinite high values per unit, improving my objective by 2, therefore making my optimal solution as high as possible, so there is no upper bound on the optimal solution. All right, so my cue is that there is an entering variable, but no leaving variable, or the ratio test does not result in a finite value for the leaving variable. Does it make sense? Okay, so hopefully, let's see whether I can. I'm doing one more attempt to see whether I can. Okay. Okay, the places are reversed, but you still don't see it. Oh well. Okay, now what I want, can I erase all of this? Okay, erase the board. Okay, now let us draw the feasible region to pinpoint exactly what is happening. So in 2 dimensions, I have x1 minus x2 less than or equal to 10, right? So if I draw it, it will be 10 here, minus 10. This is my line. And origin stays on the right side, so I have to pinpoint that direction. What about the other one? It says that x1 cannot be more than 40, which is somewhere over here. Okay, back. Let's make this 40. Okay, you can draw it much better, but that's my feasible region, right? I don't have room. Literally, I don't have room, that's why I cannot draw it. So that's my feasible region. We started again with our origin, 0, 0. S1 value was 10, S2 value was 40. That's my starting basic feasible solution. And if you go back to your tableau, we have seen that I can increase x2 indefinitely per unit, improving my objective function by 2. And there's no bound that x2 can take, right? I can make my x2 anything I like. I can increase my x2 in this direction, and I can make my objective function value better and better, all right? That's a ray of unboundedness. So I am here. If I move along this direction, I can get to higher and higher points in terms of my objective functions, and that's your ray of unboundedness. Okay, so how did you get that ray? If you go back to your tableau, you look at the entering variable, which is x2. You look at how S1 and S2 changes with respect to your entering variable. How do they change? S1 is going to be 10 plus x2. S2 is not going to be affected with x2. So this is how S1 and S2 will change if you make x2 higher and higher. All right? So if you look at the coefficients of the entering variable in negated value, that's going to be 1 and 0. This is the line of unboundedness that will take you from your origin in terms of improving directions. Okay, and that's exactly what we have over here. So if you give me any value of A could be 1,000,000 for x2, my S1 will be 10 plus x2, my S2 will be still 40. This is going to be a feasible solution, and my objective function value is going to be twice times that 1,000,000. Okay, so for any positive value of A, I can get to a feasible solution on this ray of optimal or ray of unboundedness, and I could get to better and better values. Does it make sense? If x2 is 1 over here, you get objective function value 2. If x2 is 2, you get objective function value of 4. You can increase along that direction. Does it make sense? And you will always get to feasible solutions when x2 changes using these equations relating S1 and S2 to x2. S2 is not related, it's a constant 40 anyway, but S1 will change accordingly, but you will get to feasible solutions. Does it make sense? Is that clear? So in other words, we are saying that, let me erase a little bit. Our point was x1, x2, 0, 0, 10, 40. That's my starting point, origin. I can move along the direction, the ray, this ray we're talking about, as much as I like, and get to feasible solutions. x1 value is going to remain at 0. x2 value is going to be equal to A. So A will multiply 1. S1 value is going to be 10 plus A. So this is going to be 10, and this is going to be 0. All right? So this is the ray of unboundedness. Make sense? So this is my current solution. I can change my A value to anywhere I like and move along this direction indefinitely. That's why I will get to better and better solutions. That's the Q for unboundedness. Sounds good? So we have seen alternate optimal, we have seen unboundedness, and that's degeneracy. That is next. So what will happen if I have a minimization problem? For a maximization, there is an entering variable with a negative coefficient, but the result of the ratio test is not a finite value. So I can make this entering variable as high as I like. And for minimization, there's an entering variable. There exists a positive coefficient in row 0 format. And again, there is no ratio test. Okay? The only thing that changes from max to min, Ayhan hocam, buyurun. We have a guest. Okay, the only thing that's changing from max to min, what is changing from max to min? Only the coefficient of the entering variable. We asked that it is positive now rather than negative. But beware, ratio test does not change. Okay, ratio test is the same for max and min. All right, because remember, what is the ratio test doing? The ratio test tells me how much I can move along the direction of the entering variable without leaving the feasible region. So it doesn't matter whether we are doing min or max. Again, you still want to be within your framework or the feasible region. You don't want to leave the feasible region. Then that's exactly what the ratio test is telling you. The entering coefficient makes a difference whether it's max or min, but the ratio test is exactly the same whether you do a max or min. Does it make sense? Okay, good. There is an entering variable, no leaving variable, basically, meaning that ratio test is not finite. So that's my unboundedness criterion. And the degeneracy. This was the problem, remember, with Simplex. Otherwise, life would be too easy. Otherwise, we won't have the hardship between integer programming problems and linear programming problems. We won't have that difference. So what is degeneracy? When you give me a tableau, do I have my tableau here? No. If you give me a tableau, and on this tableau, so I give you a tableau, right? I have your right-hand side values. You have your basic variables. If some of the right-hand side values, some of the basic variables have value equal to 0, that means that you have degeneracy. You have a degenerate basic feasible solution. In other words, if you have a feasible solution with one of the basic variables equal to 0, that's a degenerate solution. Okay? All the non-basic variables, of course, are equal to 0, but if you have a basic variable with value equal to 0, you also have a solution. You have a degenerate solution. Does it make sense? Now, if you don't have degeneracy, now why is degeneracy a problem? If you have degeneracy, when you do your ratio test, you can get the result of the ratio test equal to 0. Okay? So remember our formula. Where is my formula? This is a very, very important formula. Keep remembering this. The change in the objective function as the entering variable coefficient times the result of the ratio test. If the result of the ratio test is something positive, this is always positive if I have not stopped with optimality. I will always improve my objective function. I will get to a different corner point and improve my objective function. But if this is equal to 0, I can stall a little bit, right? I can stay at the same corner point for a while without actually changing my solution. A non-basic variable will enter at 0, but the ratio test will tell that it can only stay at 0, right? So it enters at 0, it leaves at 0, the vector-wise, nothing is changing. Objective-wise, again, this number is 0, nothing is changing. So we are going to be stalling if we have that. And that slows Simplex down a little bit. Moreover, there is even a bigger problem, because if I always improve my objective, I always go to something better, there is nowhere ever possible of ever getting back to the same corner point, right? I always move to somewhere better, somewhere even better. I can never get back to the same point as long as my objective function improves. But if it doesn't, and if you're stalling, staying at the same objective function value, you might be coming back to the same corner point. That's a problem, and that's actually the biggest problem that you you want to be aware of algorithms, it should not cycle, right? If you cycle, you do these indefinite loops. And there's the problem of cycling when we have degeneracy. And this is what's happening over here. If you go back to a sequence of bases, enter and leave variables, without doing any change in the objective function, 0 changes in the objective function, you might end up with cycling. This is a problem, and we indeed have an example. I don't know whether you can do this, see this. Can you see the numbers? It's in your slides. This is a very big problem. It's an example in which I have a degenerate basic feasible solution. So the starting solution here, if you look, some of the variables, some of the basic variables have 0 values. This is a definition of degeneracy. So when you have a 0 value, chances are that the ratio test will result in the 0 value. If the ratio test results in the 0 value, that means that you will gain no objective function improvement. And if you do this example at home, please go through this example slowly, you will see that you're entering the most negative coefficient variable, for example, x2 here. You're leaving the minimum ratio test result, and all of the ratio tests are equal to 0 here. You do a sequence of steps, entering and leaving variables, and then in the end, you will end up with 5, 6, and 7 as your basic variables, and they were your starting basic variables as well. Okay? So you follow through a sequence of simplex iterations, no improvement in the objective stays the same, 0 throughout, and you come back to the same point. So we have cycled, and this is a really, really big problem, and we have to be aware of this in order to guarantee that there are no cycles. All right? Make sense? Okay, let's do another example. This is more in sync with what we have been used to. This is not going to cycle, but this is still a problem that we should be aware of. So again, I have 2 variables. I added my slacks, S1 and S2 here, and I changed it to equation. I made my slack variables as the right-hand side values, but starting right-hand side value is already equal to 0. So I will start with S2 equals to 0, which is, again, a definition of degenerate basic feasible solution, right? And I will apply simplex. Simplex will tell me either x1 or x2 can enter. Choose x1 because it has a more negative coefficient. Do your ratio test. The ratio test will take either 6 divided by 1, that's one of the ratios, or 0 divided by 1. And the minimum is 0, therefore this is going to be my leaving variable. So the change in the objective function will be, it's currently 0. The entering variable supposedly will change my objective by 5 units, but it can only go to 0 value. Okay? So my objective function does not change to the next iteration. Does it make sense? Why this is a problem? It did not happen before, but the ratio test being equal to 0 tells me that this can happen. All right? So what was the vector corresponding here? I had 0, 0 as x1, x2, and s1 and s2 values was 6 and 0. What is the BFS corresponding to the second tableau? x1 is basic at 0, s1 is basic at 6, and the other 2 are non-basic at 0. All right, so it's the same vector. Nothing has changed from there to there. I was hoping to jump to a different corner point, but I'm basically stalling at the same corner point. Is that clear? And it's happening because I had a basic variable in the beginning, which had a 0 value. That basic variable exchanged roles with the non-basic variable x1, but 0 exchanging roles with another 0, and no change in the next vector. So I'm at the same solution, in other words. So if you want to draw it graphically, this was the origin. My first starting point, x1 and x2 was equal to 0. That's corresponding to this BFS. The next one also corresponds to this origin. x1 and x2 are also equal to 0 there as well. So I do one step of stalling at the corner point, which is the origin, and then I am able to jump to the next one. Yes?
How can we understand the values of x1 and x2 from the table?
They are non-basic. Anything which is non-basic and not these basics are supposed to be equal to 0.
And x1 and x2?
S1 and S2 are the basic ones, and they have the right-hand side values in the tableau. So if you go back to here, you have, in standard form, you had S1 equals to 6, right? S1 minus x2 plus S2 equals to 0. You said that I am going to have my S1 and S2 as the basic variables, S1 for the first equation, S2 for the second one. The others are going to be non-basic. They will have 0 values. Right? So the ones that you see in the rows of the tableau are your basic variables. And their values are on the right-hand side. The ones that you don't see are your non-basic variables. All of them are equal to 0. Okay? And you pick one of the non-basic variables at every iteration and ask, is it eligible to enter? Would it be better if I make it from 0 to something higher? That's your own option, right? You can make it positive. Will it be better if I make it positive? That's the question you will ask. Does it make sense? What the degeneracy is, why is it a problem? It's making us stall, so I sort of did a void, empty, simplex iteration. I was hoping to jump to a neighbor. I stayed at the same thing. I did my exchange, but it was an empty exchange. The vector-wise, nothing has changed, okay? But then I was able to jump from this corner point to this one in the next iteration. So it wasn't as bad as our first example. I did not come back to the same point, at least. I was able to jump away from this basic feasible solution. And indeed, this is the optimal one as you do in this next iteration. But this is something we have to be very careful about, the degeneracy. So as soon as we know that there is the potential of having 0 on the right-hand side, as soon as I have a degenerate basic feasible solution, I have to apply some rules to not to cycle. Okay? Now, in the first example that I give you, and in the cycling example, the right-hand side was already given in a form in which I had a 0 starting point. Okay? So the question is it only the case that if I give you a 0 in the beginning, that's the only way of ever having degeneracy? That's not actually. It can come up at an intermediate iteration as well. And let's look at how it can arise in this very simple example. So let me draw it. So again, I add my slacks just as usual. I convert this to an equation. 1 minus 3 minus 9, 0, 0, 0. Please help me on this in terms of the numeric calculations. 1, 0, 0, 1, 8, and 4. Okay? That's my starting tableau. Which variable will enter? X2 will enter. Which variable would leave? I will look at my ratio test. I will have 8 divided by 4, the coefficient of the entering variable, versus 4 divided by 2, the coefficient of the entering variable. So which means what? I have either 2 from here or 2 from there. Which means what? There's a tie. So remember, what does the ratio tell me? If you enter the variable x2 and if you make it as high as the result of the ratio test, then this variable, which gave the ratio test the minimum value, is going to hit 0. Now, in the next iteration, not only the one that you choose, but the next one is going to also hit to 0. So there will be an exchange with only one of them, but both of these values, S1 and S2, will drop to 0 in the next iteration. Okay? And if that is the case, one of them is going to remain at 0, and that will also be causing a degenerate basic feasible solution. Does it make sense? So in the next iteration, if you do your simplex, which one would you like to leave? X2 enters, so both of them can leave, right? Let's say that you want S2 to leave. What would happen in the next iteration? This will be S1, this will be X2. What will be the value of X2? It will be the result of the ratio test, which is 2. Okay, you should do these calculations at home. What about S1? If X2 becomes 2, look at this equation, and look at this equation. What will be the value of S1? S1 equal to X2 equals to 0, X2 equals to 2, X1 will remain at 0, S1 will be equal to 0. So you will get a degenerate BFS. All right? So in other words, you can get degeneracy in the middle of simplex method. It doesn't have to be degenerate from the beginning. As soon as you have ties in the ratio test, this was the case, right? We had two potential leaving variables. Either one of them would result in a 0 value, but the other one will be basic and 0, just like S1 here. So I have degeneracy at this point onwards. Right? So please fill in the gaps for the simplex method. But if you have degeneracy, you have to beware because you can have cycle. And there's a simple rule, Bland's rule, which simply tells you that order your variables. Don't call them S1 and S2, call them X3 and X4. All right? If there is the potential of cycling, always favor the smaller index variables. So do it in an orderly fashion. Always enter the variable which has the smallest index. Always, whenever there are ties, of course, always choose the minimum. But if there are ties, just like in this case, I wouldn't favor S2, but I would favor S1. If you do this, then you won't ever cycle. So go back to this cycling example and do it as an exercise using Bland's rule. And that will guarantee that you won't come back to the same thing. The only change will happen in the very last tableau. Instead of X6 as the variable to enter, you will choose X1, and there won't be cycling. You see that Bland's rule is going to free you of cycling. But degeneracy we have to be aware of, and that's a big problem. That's the only way simplex slows down. Otherwise, it just jumps from one corner point to a better one. All right? Okay, please start doing the homework. I am always available. Me and my friends are always available through Piazza. So start. You can come today or tomorrow. Make sure by after spring break, you know everything about simplex, because the practice session and the next quiz is going to ask you all the details about simplex, not just the brute force elementary row operations. We won't ever ask you to do pages and pages of elementary row operations. We will ask you questions to pinpoint whether you really understood the ingredients of the simplex method or not. All right? So ask questions if you like on Piazza. You can discuss among yourselves as well. Okay, see you then. Have a good break. Keep safe.